Welcome everyone. I hope you can all hear me. If you can't, please let me know in the chat box. So this is a very special virtual talk hosted by the Center for Astrophysics, Harvard and Smithsonian. Some of you may know me from our public observatory nights. If you do, hello again. But for those who don't know me, my name is Philippe, and I am the outreach manager here at the CFA. And I'm also a former researcher of astrobiology. So my role here at the CFA, honestly, is to be honest, it is my dream job. This is a dream. I love what I do, and that is bringing exciting science to the public and fostering new generations of scientists, but also tackling misinformation, something I'm very passionate about. So we have two very exciting talks for you tonight. After our guest speakers give their talk, we'll have some time for questions. If you want to submit any questions during the talk, then please use the Q&A button at the bottom of your Zoom screen. You'll see a little Q&A, little button. Use that for submitting your questions. As soon as you have a question in mind, feel free to just add it into the box. So that way, when we finish the talks, we'll have a whole list of questions ready at the get-go to give to our speakers. If you have any kind of technical issues, then for that, please use the chat box, not the Q&A. So we aim to kind of wrap up at around 7 o'clock. So that's kind of the time frame. I should also say this is going to be a very fun talk. It's going to be relatively informal, and both of our speakers are going to be presenting this talk at the same time. So it's going to be quite a fun and engaging style for this talk. So without further ado, I'm going to introduce our guest speakers, who are Andrea Sacchi and Ole König. So first of all, Andrea Sacchi, so he did his PhD at the University of Florence, studying X-rays from accreting supermassive black holes with Professor Guido Risoliti. He is currently a postdoctoral research fellow at the Center for Astrophysics, where he explores the nature of a plethora of accreting systems, from white dwarfs to stellar mass black holes to supermassive black holes. Very exciting. Our other guest speaker tonight is Ole König. He did his PhD on accreting compact objects at the Friedrich Alexander University Erlangen-Nuremberg in Germany with Professor Shaun Wilms. He led the discovery of this very exciting nova fireball phase, which was featured on the cover of Nature. Very impressive, using the X-ray Space Telescope E Rosita. He spent the last 6 months at the Center for Astrophysics as a visiting scientist and will return in December to work with Jack Steiner on accreting black holes. Both Ole and Andrea are true experts on tonight's topics, which is very exciting. And the topic is T Coronae Borealis, or T-Crib for short, and its explosive nova activity. They each bring personal insights and direct research experience to their presentations, offering us a unique look into this fascinating phenomenon. Right, Ole and Andrea, the floor is yours. Take it away.
Thanks, Philippe. Thanks for this great introduction.
Yeah, thanks.
Yeah, I'm very excited to be here tonight. I'm connecting from Germany, saying hi over the Atlantic. And let's jump into it. So novae are new stars that... Andrea, can you forward the slide for me?
Yeah.
Doesn't seem to work for me. Thank you. Novae are new stars, new star-like light sources that emerge somewhere on the sky and then stay bright for a couple of days or weeks, sometimes even a little longer, and then fade away again and go back into quiescence. So these events, they have been known and observed for literally thousands of years. The first recorded nova was by Chinese astronomers or astrologers at the time in the 4th century BC, so more than 2,000 years ago. Another quite interesting event was 5 years before the year 0 that was observed by Chinese and Korean astronomers. And this event gave rise to the possibility that a nova could actually have been the Star of Bethlehem. I should say that there are a lot of other hypotheses for this astronomical event. So I won't go into a lot of detail here, but this is one possibility. Then the term novae, this is a Latin word, was coined by the famous Danish astronomer Tycho Brahe, who observed one of these new light sources in 1572 and published this in the book De Nova Stella, which is Latin for concerning the new star. However, until the 1930s, the terms nova and supernova were actually used interchangeably. The physics behind this event was not yet understood well enough to distinguish what a nova and a supernova is. And tonight we're also gonna learn what this distinguishment, the difference here is. Now, since the 1960s, we know that novae are thermonuclear explosions on the surface of a white dwarf, a stellar remnant. This is what we cheekily referred to with the hydrogen bomb. So what are we gonna, next slide, please. What are we gonna do tonight, and what are we gonna talk about? Firstly, we need to understand how a nova system is produced. We will go a little bit into stellar evolution, what white dwarfs are. We're going to talk about the physics of the hydrogen bomb, of this nova explosion, the thermonuclear runaway. We will talk about how to detect such systems, so about telescopes, but also about the really crucial role that amateur astronomers play. And then we will talk about this specific event that is upcoming, T Coronae Borealis, that is extremely exciting for all of us researchers, but also for the general public, in my opinion, when it will erupt and what we can learn from it. And we will close off with how can you get ready if you're interested in this event.
Okay, I'll take off from here and I start with tackling the first point of these, such as to understand how a nova is produced. Ole mentioned it's a thermonuclear explosion over the surface of a white dwarf. So let's start understanding a bit what a star is, how it is formed, and how do we get to such a system. So stars are formed in these beautiful environments, which are nebulae. And you can see here the pillars of creation observed by JWST and the Orion Nebula imaged by HST, the Hubble Space Telescope. And in these environments, you have clouds of gas, and a cloud of gas may stay there for a long time, but also could randomly contract and expand. And if it is big enough, so you take a cloud, and if it's big enough, when the contraction starts, it doesn't stop. And so as it is contract further, as you know, when you contract a gas, this tends to heat up, and so it might heat up again, contract again, heat up again, and at a certain point, you arrive at the center to such a temperature that you can start fusing material, and you have basically a star. So when I say core and when I say a star, of course, the closest star to us is our own sun. And by fusion, I mean that in the core of the star, you have nuclear reaction where you take lighter elements. You have here a periodic table that I'm sure you're all familiar with, but just to be extra sure we are on the same page, you have at the top lighter elements, and then you have heavier elements when you move to the right, and you go down this periodic table. So when I say fusion, I mean that you take lighter elements like hydrogen and helium for the vast majority, and you fuse them together to get heavier elements. And when you do these, you free energy, you liberate energy, and this energy radiates out from the core and counteracts the self-gravity. And by self-gravity, I just mean the gravity of the gas itself that composed star. And this system is in equilibrium. You have energy that radiates out, you have the pressure of the gravity that pushes it in, and everything is in equilibrium. It is in equilibrium until you arrive at the fusion of iron. Why? Because iron is the most stable element of this periodic table, and so if you try and fuse iron, instead of getting energy out, you have to put energy in. And this is unfortunate if you are a star, because you cannot sustain the equilibrium anymore, and so you go further on the life stages of the star. Now, this is sort of a schematic of what happens when you have different mass to start with. And the regime we are interested into is this one. So we are talking about a star with a mass which is comparable or slightly lower than our own sun. And you can see that after this period of the stellar life where everything is in equilibrium and you are just using the fuel in its core, namely hydrogen, once you run out of that fuel in the core, you go through a different phase, which is called red giant, where the star puffs up and start sometimes pulsating, liberating material, and this creates these beautiful nebulae. I hope you can see my cursor in this phase, which are called planetary nebula just for historical reasons, but has nothing to do actually with planets. And what is left behind after this phase is just the core, in which no more fusion is going on, so it is not actively producing energy, but as it is still holding on the heat that was characterizing that system at the beginning, because we are still talking about something that was in the core of a star, and so it is hot, it's still bright and radiates heat. And then with time, it will radiate away all the heat and just sit there basically forever. This is if it is an isolated system, but if it is in a binary system with another object, for example, another star, etc., things might change. It is also worth noting that Ole mentioned before the difference between novae and supernovae. Supernovae are much more energetic, that's why super, and are usually produced by the death of the larger star, or by the fusion of two white dwarfs, because a white dwarf structure is sustained basically by the fact that you cannot push the particles that are composing this star too close together. But if the pressure is high enough, for example, if you dump too much material onto a white dwarf, then these might in fact explode, and these explosions are one type of supernovae. So T Coronae Borealis, which is the system that we are talking about tonight, is composed by a white dwarf and a red giant in a binary system. And by binary system, I just mean that these two objects are orbiting around each other. These systems are known as symbiotic stars or symbiotic binaries, and one of the most famous one is these R Aquarius system, because it's close enough that you can imagine it, and we can see this beautiful structure, which is none other than the planetary nebula that I was referring before. And actually, this nomenclature symbiotic star is pretty recent. It's just been used in the last 50 years or so, but it was known much before that. In particular, it has been discovered by Annie Jump Cannon here at the Harvard College Observatory, observing the emission from these stars. She could tell there was signatures of two different objects, namely the red giant and the white dwarf. And so it was clear already almost a century ago that these systems were particularly interesting. Now, you can see here that here in the middle, you have material passing from the red giant onto the white dwarf. And this happens because in this point, you can see here that basically the attraction that a particle, a test particle, would feel from the red giant is equal to the one that it would feel from the white dwarf. And so if it's just a bit closer to the white dwarf, just randomly, it would just fall onto that. And I mentioned before that nuclear fusion is not going on anymore on a white dwarf, but you still have material falling onto it, and this is the material that actually we are interested into.
Yeah, exactly. So we have a system where more and more material, more and more hydrogen is dumped onto the surface of the white dwarf. And something has to happen with all of this hydrogen. So if you could forward to the next slide. So I mentioned the thermonuclear explosion. If you pile up more and more material on the surface of this roughly Earth-sized white dwarf, then the temperature and the pressure will increase and increase and increase. And at some point, a critical mass threshold is reached. And at that stage, the thermonuclear fusion is triggered and ignites. And then the shock wave or this energy, like the fusion zone, quickly goes around the whole white dwarf in this shell of material on the surface and then bubbles to the top. And this is an unstable process, so it can't be stopped. You will inevitably blast off this shell of material. That is called a runaway process. And right when the energy is at the top of this white dwarf on the surface, you have essentially a hot glowing fireball. And that's the reason why this very early phase is also called this fireball phase. Now, then the envelope is ejected because the escape velocity of the material at this stage, there's so much energy in the system that the escape velocity of the material is way bigger than the gravitational attraction. So it's blasted off with enormous speeds, which can be hundreds to thousands of kilometers per second or miles per second, if you wish. Next slide. And what happens then if this envelope expands? Well, let's take maybe a little comparison. If you have a insulating mug with the coffee, then the heat of the coffee can only escape on the surface. And if that surface area is relatively small, it will stay hot for some time. If you spill it, then it has a much higher surface area, so it will cool down much more quickly. And well, something similar happens with the envelope. You have a larger surface area, so it cools down. And I mentioned this fireball. So what you have is it's black body radiation, which is like a Planck spectrum. If that tells you something, it's basically like if you have a piece of hot glowing iron that radiates with black body radiation. And at first, the peak of this radiation, you have most radiation in the X-ray regime of the electromagnetic spectrum. This can be seen here on the right-hand side. Yes, the visible light are the colors, and then this black, exactly, the black line, that is basically the distribution of the light, the energy distribution. And then as the envelope cools down, it is shifted to lower energies. So first into the UV band and then into the optical band. So you can see that a lot of the flux is now in this colored regime. Exactly. Thanks, Andrea. And when that happens, that usually triggers the discovery when the light is most intense in the optical light. So what we can also see with the with our own eyes. And then there are a lot of other phases that I won't go into detail, but there are shocks with the interstellar medium. There are winds that potentially clash into each other, interaction with the companion star. So there's a lot of exciting physics that is happening in the later stages as well. Next slide, please. Now, how can we detect such a system? Usually, the discoveries of the more faint novae are through optical surveys. This is one at the Ohio State University called Assassin. And these surveys, these types of surveys detect roughly 10 novae per galaxy per year, so 10 novae in our Milky Way. It is estimated that there are roughly 50 novae going off, but some of them are behind some clouds of material, so we can't actually see them, and only 10 make it through to our telescopes. Next slide, please. Well, I mentioned in the beginning, there is, for the bright novae, there is a really essential contribution from amateur astronomers as well. Sometimes for the first few days, there's no data with these optical surveys, as was the case in this Nova YZ Reticuli that we studied a few years ago. The first few days were recorded by an amateur astronomer in Australia, and he reported these data points to the American Association of Variable Star Observers, AVSO. And only with these data we can analyze our event properly. So amateur astronomers really play an essential role also in contributing to the science of these events. Next slide. So I said the nova has signals all across the electromagnetic spectrum. Essentially, I mentioned this black body radiation, and essentially most of this phenomenology can be explained as because it shifts, the spectrum shifts in the wavelength range back and forth. So first it is visible in the X-rays, and then later in the optical, and then in fact it actually shifts again. So later we have X-rays again. And also other wavelengths like infrared or radio. Now, I am an X-ray astronomer. So next slide. So I am particularly interested in the very early phases and measuring that with space-based X-ray telescopes. So one telescope that we use a lot is the NICER telescope on board the International Space Station. And with this telescope for T Coronae Borealis, we hope to catch this very early fireball phase, which is extremely challenging to catch because, as we will later see, we don't have a precise eruption date. We only know, okay, it will erupt like plus minus a few months. And this very early phase is quite short, only a few hours. So because it happens before the optical light is emitted, it's quite difficult to catch it, and we need large monitoring programs, which we currently have in place for T Coronae Borealis. Next slide.
Okay, so Ole mentioned that amateur astronomers are crucial in this kind of science because, of course, you have much more eyes watching the sky, and these objects are actually bright, even for a human eye. Okay, so let's talk a bit about when was T Coronae Borealis discovered before. Another thing that Ole mentioned is that novae appears and then disappear, and some novae just never appear again, and those are just called novae. But in the case of T Coronae Borealis, this is actually called a recurrent nova because it recurs again and on a pretty stable timescale. So the last time it was visible, it was in 1946, and it's actually interesting that it was independently observed by three amateur astronomers independently. The first one was Kamenchuk, and unfortunately we learned about his discovery only 5 months later because he happened to find himself in the middle of Siberia. And so he sent a mail to Moscow announcing the discovery of a new nova, but it took 5 months for the news to be published. So these novae exploded in February, the beginning of February, and actually the news from Kamenchuk was published in May. Another astronomer, another amateur astronomer was Knight, and he was in Stoneleigh, and he was, you can see here actually a piece of paper he wrote himself, writing to communicate the discovery of the nova. And you can see here that he says that his eye was literally struck by the eye of the nova because he was observing another object in the same constellation. And so you can imagine that if you expect to see something very faint in the constellation, and then all of a sudden, bam, there's a nova there, you're clearly caught by surprise. And after he notified the Royal Society, he was told back that actually it was in the same position of a nova that was observed roughly 80 years before, in 1866. And so this is why the recurrent nova. But actually there was a third independent observer, such as Woodman, somewhere in Wales. And the interesting thing is that Woodman is actually still alive, because at the time of this discovery, he was 15. Apparently, he was waiting for his dad to come home, and because the train was delayed, he decided to stay up all night waiting for his dad, and at a certain point, he was just out observing the sky, and he was an aficionado, and he realized that there was an extra star, an extra source of light in a constellation that he knew very well, the Coronae Borealis. And so, yeah, he actually discovered it before night itself. So that's extremely interesting. And for this author, Shears, actually interviewed him in person last year. And Woodman says that he still recalls the event extremely well at 94. Before that, I said it was observed in 1866, always in the northern Europe, in Ireland, by an amateur astronomer, Birmingham. And interestingly, it was after this that people went and checked back if this source was observed even before, because again, we said it's a recurrent nova, and just by doing 1946 minus 1866, you get about 80, and so you can check whether 80 years before it was observed. And they discovered that actually it was by an English astronomer, Wollaston, that mistakenly associated it with another star, but a new analysis was able to distinguish the two stars because they're too far apart for it to be just a mistake. And so this is almost surely another detection. And actually, going further back, there is a chronicle by a German monk, Burchard von Runsberg, that actually they reported that in 1217, so in medieval time, there was a bright source lighting up, a new nova, lighting up in, he called the Ariadne crown, which is another name for the Corona Borealis constellation. And we, of course, cannot be 100% sure that it was really the T Coronae Borealis nova, but we have very good insights because the timing, it's close to when it was supposed to blow off, and also because usually for we can exclude other events. For example, if it was a supernovae, we would still today observe some of the remnant of a supernovae, and on the other hand, if it was a comet, it would have be recorded as a bad omen, while Burchard says that he saw a new light and it was a good omen, and so we can be fairly sure. And so, as I mentioned, the current time is about 80 years. Last time was in 1946, and so if you do 1946 plus 80, you get 2026, which is pretty close to today. And actually, we know a bit more even.
Yeah, now of course there are telescopes of the whole world. Telescopes are monitoring this event, and we have gathered quite a lot of data. So what I'm going to show here is called a light curve, which is the brightness of the source of this position on the sky as a function of time. And you can see two different colors. These are two slightly different energy bands. And you can see that in the 19th century, 1866, you have this spike in the data, exactly. And this points to the explosion that was visible by the bare eye. It was at 2 magnitudes. Andrea's going to talk about that a little, about the brightness later a little bit. And then it was in quiescence again, but in 10 years before the eruption, the high state began, which is somewhat of a mysterious, next slide, please, somewhat of a mysterious elevation in the brightness that is not super straightforward to explain, but this happened roughly 10 years before the eruption in 1946, and it has also started in 2015. So this was a first indication, hey, there is something going on. Next slide. And if we look at the more recent data, we see that something has happened that we have also seen in 1946, or not me personally, of course, but researchers. And this is called the pre-eruption dip. And this pre-eruption dip, the source basically dims a little bit. It becomes a little bit fainter before it then blasts off, roughly 1 year before the eruption. And quite a similar trend is visible now. It has begun in March 2025. So that based on this pre-eruption dip, the most constraining eruption dates have been suggested. And it was suggested that it erupts in this year, actually between spring and summer, which is now already gone. So apparently it has not yet erupted, which is quite interesting because it may point to some slight offset in the periodicity. It may point to some correlation with the orbital periodicity. So some researchers have suggested that 2025 is also a possibility. And some have even said 2027, which I think is rather unlikely based on this pre-eruption dip, but it shows it essentially shows the difficulties to predict an event that is somewhere in the Milky Way, 3,000 light years away. But overall, I think we can say that this nova is going to go off in the next year time frame, and most likely in the next months. I think the prediction of 2024 is still based on this pre-eruption date, is still quite valid and seems to be the best indicator for the eruption. So let us have a quick look at the scientific prospects that we can learn from this nova. Novae can be progenitors of supernovae, a particular class of supernovae called type 1a. And the crucial question here is, how can a white dwarf grow in mass until it reaches the Chandrasekhar mass limit, this mass threshold, this limit above it will explode completely in a supernova? Because we have seen that if you dump material onto the white dwarf, it periodically erupts in a nova, so and blasts off the material. So it's quite hard to retain material on the surface. But there are mechanisms for that, and T Coronae Borealis will help a lot in understanding that. Another point here is that novae, the thermonuclear fusion process produces neutrinos. These have been seen from the sun, but they have never been seen from a nova. So that's super exciting because there are not a lot of extrasolar sources of neutrinos known and detected at high rates. And the point that I'm really interested in, I mentioned it before, is the detection of this fireball phase in X-ray light, which would allow us to measure the initial velocity of this expanding shell. So how fast, how many hundreds of kilometers per second is it accelerated, and how quickly does it crash into the companion star, for example, or the interstellar medium? And how quickly does it cool down? Next slide, please. So there are a lot of in summary, there are a lot of different science cases and very exciting science cases because the source is extremely close. And Andrea will now show you where it is on the sky and how you can find it.
Yes, just a quick notice here, the source actually entered the pre-eruption dip in 2023, not 2025.
Oh, yeah,
that's why we know it is approaching. It is not a thing that we are going to observe in the future, but we already observed this dip. So that's why the prediction. Okay, so if you want to go out and look at the starry sky and search it for yourself, this is where you can find it. So if you can locate the Big Dipper or Ursa Major, as it is probably better known in Europe, which is also the same constellation that is used to locate Polaris. If you take the one of the sides of the Dipper and you prolong it up, you can find Polaris. But actually, if you take let's say the handle of the Dipper and you prolong it back, you can find a bright star in the constellation of Bootes, which is actually right above Arcturus, which is one of the most bright star in the northern sky. And the Corona Borealis, the constellation, you can find it right above that. Okay, now of course, T Coronae Borealis is not visible by naked eye right now. It is only visible by telescopes, as Ole was mentioning before. But when it will blow off, you will be able to find it here. Now, when I say brightness, what do I mean? You can see here the way astronomers, at least in the optical band, they usually classify how luminous, how bright a star appear in the sky is called magnitudes. And it's a weird scale where the negative values means that the object is actually brighter. And so you can see the sun here as a magnitude of minus 27 roughly. The full moon is about minus 13, minus 12, and Polaris is about at the second magnitude right here, and T Coronae Borealis at its peak brightness will be as bright as Polaris, so extremely bright. It will be definitely visible by the naked eye, and for a comparison, it will be the brightest nova since a long time. In the latest bright was in 1975, and still it was not particularly bright, that one. It was only a magnitude, a third magnitude, which means that was 6 times fainter than how we expect T Coronae Borealis to be. Now, Ole will tell you something about how can you get ready to observe that.
Yeah, so we've seen it's going to be, for astronomical standards, it's going to be an extremely bright event. It will be among the brightest stars in the sky at the peak magnitude. So if you have a telescope, you will maybe be familiar with these lookup tables, these photometry tables. These can be found on a lot of different resources we found on the internet. There are astronomers' forums where people exchange their thoughts and their observations. And if you are an telescope enthusiast, and if you have one and are interested in observing it, you can go into these forums and exchange ideas. There are also apps that you can download that will give you basically like a trigger alert. As soon as the nova goes off, you'll get a notification. And these are ways to interact most quickly with the scientific community, potentially. Next slide, please. So we have seen that novae are extremely exciting events from the physical point of view, from the historical point of view, and also from the basically population point of view, like how ordinary people, how all of you, like non-professional astronomers, can experience this event with the naked eye, just in their backyard. I hope you liked this introduction to novae and T Coronae Borealis. And with this, I would say we end the talk, and we are happy to take any questions that you might have.
Yeah, and to add on that, like observing yourself this kind of event will place you in a uninterrupted line of observers, of human beings that went out there and observed this event in history, and I think that's just beautiful. So I can see a couple of questions in the chat. I don't know, Philippe, if you think we can read them out loud and answer.
Yeah. So
okay.
First of all, thank you so much for an amazing talk. Really, really interesting. Yeah, I have a couple of questions myself. There's a couple of questions in the chat. I'll start with a comment, not so much a question, but for those familiar with Boston, or for those who live in Boston, I was actually cycling down the Esplanade the other day, and there was this massive bright light in the night sky that was like really, really bright, and I was so convinced that it was this nova. And I immediately stopped cycling, and I took out one of these star maps, and I pointed it at this bright light, and it was not the nova. It was actually just Venus. Very, very
Actually,
bright.
the same happened to me tonight. I was like, just like seeing one bright star in the sky, and I was like, is that it? Is that it?
Yeah, me too. So yeah, for those who haven't seen it, yeah, Venus right now is insanely bright, but it is not the nova, not yet. So let's see what some of the questions we have. So we have
Also, just if you didn't have time to scan the QR codes that we showed earlier, don't worry, we are happy to share the slides, and we have actually a bunch of other useful links that if you're interested in learning a bit more, we can share.
Yeah, great. That's a great comment. Yeah, well, what I'll do is I'll share those slides to everyone that attended this this talk. So thanks for that, Andrea. Yeah, so we have the question about the so we already clarified that there was a slight typo with the slides. It was actually 2023. So I'll just skip over them for now. What do we have? So we have is there an organized effort to monitor T Coronae Borealis continuously? What procedure is in place to get the word out once it goes nova? By Rudenko.
I think Ole is the best person to answer these.
So there's a collaboration of scientists working on novae who have coordinated their efforts to make sure that in all the different wavelength ranges, I mentioned the electromagnetic spectrum, so we want to look at the event with many different telescopes, and coordinating that is challenging, but it is in place. And it is somewhat of an effort because the time scale is not quite clear. I think from my point of view, I somewhat expected an eruption this summer. So I proposed for quite a quite a short cadence, like many observations after each other. And if you extend that far into the future, it's kind of costly. So I think now that it hasn't yet happened, I would say we're still eagerly anticipating that it happens. So I think we're going to continue with this monitoring cadence, but it's challenging if it doesn't go nova soon, I would say. What procedure is in place to get the word out? I would say the best way is probably these apps. I must confess I haven't tried them myself, but I would expect that as soon as someone sees an entry in, for example, the Astronomer's Telegram, which is a forum for or like small non-peer-reviewed publications that people can put out quite quickly. As soon as something happens there, or in some of these automated surveys and some triggers are put out, then this will be forwarded to these apps.
Great. Thank you so much. Let's see what we have next. So we have by Henrik Bodmer, we have, how do you predict the expected brightness of the event?
Yeah, maybe I can answer to this one. Basically based on the past events. So we know how bright it was in the past. We expect somewhat to be as bright as back then. And actually, that's why it is important to have amateur astronomers, because when I mentioned that three independent discovery were done, of course they didn't happen at the same time, and so we can trace the very first moments, how bright it was, how it evolved, and this is extremely useful for scientists, and can inform us what to expect. So that's how we know.
Yeah, I think this nova could really be one of these cases where the amateur astronomers are faster than the telescopes, maybe.
Yeah, definitely.
Which is cool, which is really cool, I think.
Yeah.
All right, we have Ari that says nice presentation. Thank you, Ari.
Thanks.
Julio says, how can we kept updated on this event? Is there an email distribution list? Well, I guess
Yeah,
maybe I can answer that.
yeah, we answered the first question, but I think the email distribution list, that's I think we could, as soon as we know that it is there, we could send something out.
Yeah, no, it's a really good point. Actually, just a little insight into my job is that I'm actually working on a newsletter that is intended for the public, for coming from the Center for Astrophysics. So for everyone who got an email from me about this talk, then you'll automatically be subscribed to this newsletter, and so hopefully once that comes to fruition, then I'll send it out probably like once every, maybe bi-weekly, and so in there you'll expect to know when this happens. So
Well,
yeah,
if it
sorry.
happens, we have to send it out quickly, because it will be at the peak brightness. It will be there only a couple days.
Yeah.
So
Yeah.
yeah, it will be visible by bare eye only maybe 3, like based on the past behavior of T Coronae Borealis, maybe 3 days, maybe 5.
So we have just a few minutes left. Christina asks, was there any astronomical event that inspired you to, oh, sorry, it disappeared. Where did it go? Was there any astronomical event that inspired you to become astronomers?
That's an extremely good question. I can't, well, I know of one event where my high school teacher took us to an observatory, or I think it was like it was a hill where they replicated the solar system in real scale. So you had the sun as maybe like this big in the center, and then it was a whole hike. So because the solar system is pretty big, so you could explore the other planets. And I remember we went there in the night and I was maybe 6 or 7, and I think that really got me enthusiastic. But I've always been kind of interested in space stuff, so I don't know if that was like shaping.
No, in my case, unfortunately not. I was just always unknowing, the kid that would ask questions, and yeah, that was about it. It was a very terrestrial occurrence that pointed me towards astronomy, such as that no other class were as interesting. and that's about it.
Sometimes it's the professor or
Exactly.
something like that.
Maybe your local outreach manager, right?
Maybe.
Okay, great. So Chris asks, given the mass of the red giant, how many more reoccurring events are possible in the future before the symbiotic relationship can no longer take place? It's a great question, Chris.
I think the limit is not the mass of the red giant. Definitely, because the mass is actually not that much to ignite the thermonuclear reaction. So what will happen before that, not of course on human timescales, but let's say in the general course of events, it will be the red giant that will end his life and probably become another white dwarf. And so you will have a system with 2 white dwarfs, and that might evolve. Maybe they're gonna merge in the distant future. Probably not, because it's pretty separated as a binary. So the 2 objects are pretty far apart one to each other, and so they will just cool down over cosmic timescales and just be there forever.
Yeah, I agree. The typical rates of material dumped onto the white dwarf in novae, the so-called accretion rate is, I believe, 10 to the -5, 10 to the -7 solar masses. So it's going to be limited by the life of the red giant.
All right, the next comment is someone who came to the observatory night recently. Elaine, welcome, welcome. Yeah, I'm glad. I hope you, well, sorry, maybe you didn't come to the observatory night, but you're observing the comet. We had a comet-themed observatory night here at the CFA. So hopefully you saw this bright light there. And then you asked, what could it be? Oh, yeah,
I'd say it was a satellite.
yeah. Was it
It's
moving? Yeah,
it's probably the the most likely explanation. It was
yeah.
just a satellite, and maybe you caught it, especially when it's not too late. And if I remember correctly, the comet was visible pretty early in the night. You have this effect for which, if you have an object which is far from Earth's surface, it might still be illuminated by the sun. Well, that was exactly the case of the comet, basically. And so it, like, the solar panels might reflect light, or the body itself of the satellite. So that was probably it.
Right, we are just over 7. I'm going to take a couple more questions, and then anything that didn't get answered, I really apologize, but we all of these questions are going to be forwarded to our speakers, and then they're going to answer them themselves, and then we'll send all of the unanswered questions with answers to everyone that attended this talk. So your questions will be answered. I'll just do just a couple of more. So we have anonymous attendee. Great talk. Given the lengthy timeline scales in the universe, how can you be sure you haven't missed the event? At what point do you decide it's time to move on from an expected event?
Yeah. So I would say something at this brightness is definitely going to be observed. I think it will be noticed. So I think we can be pretty sure that it hasn't happened since the last eruption in 1946. At what point do you decide it's time to move on? That's a tricky question. I don't know. I don't know how to answer that. It's gonna be in the back of people's minds, and they will look at the data of the monitoring programs, and maybe at some point, if it hasn't exploded, which I don't think, in the next 2 years, and then people will maybe stop their expensive monitoring campaigns, but the more shallow monitoring campaigns, they will still be in place and people will still look at it.
I totally agree. It's always a matter of cost benefits, and at a certain point, you just evaluate what are the resources that you have, how many you can put in one science case, and if there are better science cases, and that's it. But it's the community that decides, in the person of who manages the telescopes, etc. But it's the community that decides this.
Right, I'm gonna take just one more question because we are over time. So I'm really sorry for those that haven't been answered. But like I said, you will get your questions answered in due course. So the final question we have in chronological order is, it's a juicy one. Would the expansion of the universe or relative motion of our galaxies affect the apparent period of nova events? By Gavin.
I would say no.
All right. Anything to add, Ola?
Maybe Ole can tell me wrong, but I don't think it's
I
relevant.
absolutely agree. This is an event in our Milky Way. It's 3,000 light years away, which is very close. It's like, I think, roughly 1/10 of the distance to the center of our Milky Way. And on this scale, the expansion of the universe has a negligible effect.
And furthermore, the motion of our galaxy, even if you think like that we are orbiting around the center of our galaxy, all objects this close, we will more or less travel together. And so even in that case is not much relevant.
All right, it's 7:05. So everyone else, you get
The
your
last
questions.
question, max brightness will be 2 magnitudes. So
Thanks.
as bright as Polaris.
Yeah.
That was a quick one. Sorry, Philippe.
No problem. All right. Well, thank you so much again. It was really, really interesting, and I'm looking forward to seeing this thermonuclear explosion in our night sky. So thank you so much. Everyone else who's still on the call, hopefully we'll see you at one of my observatory nights or any other outreach event that I have planned, and hopefully you'll hear from me soon via the email mailing list. So until then, have a magical day. Keep looking up, stay curious, and I'll see you in the next one. All right.
Thanks, everyone.
Ciao, ciao. Have a good
Sign
night.
out. So farewell. Okay. Bye, everyone.